It has like one charge.
So
On the periodic table.
yeah, if it doesn't tell you in brackets, then you'll assume a plus one. That's right. Yeah, but for this one, that's a good question. That's why when you have brackets and it tells you there, that's the charge that you gotta use. If it doesn't have brackets, it's a one.
Number 3 doesn't say anything, so we're going to use the charge from the periodic table.
Plus one. Yeah, so aluminum then will be a plus one for aluminum here.
Minus 3.
Aluminum can be a plus three.
Plus 3 again.
Yeah, but aluminum can also be a plus one. So in this case, it doesn't have anything in brackets. So then you'll use a plus one, and sulfide is a minus 2.
Yeah.
So then you'll have Al plus sulfur 2 minus. So what do we have? Al2S. That's it. Aluminum sulfide. If it says aluminum brackets 311, then you'll use a plus 3. Yep. And lithium plus 1 plus oxide, lithium Li2O. Remember, do not use the mono, di, tri, and all those prefixes if it's ionic. Okay, and these are all ionic so far. Okay.
Ionic is what again?
Ionic, you'll know it's ionic if you have a plus and a minus. Yeah. And you can look at it on the periodic table. Okay, where aluminium is, yeah, it's a plus 3 on the periodic table. Usually we've been using a plus 3. That's the easiest charge that it assumes. But if it doesn't tell you here in brackets, you'll use a plus 1 for that metal. Yeah, aluminum can be a plus 2 as well. Some of the reaction, remember we looked at something where it was PbO3 or something like that, and there's other forms, so they can form those different charges.
Isn't aluminum a minus 5?
No, aluminum
Same story on the other side?
on the periodic table it says 13, right? So 2, 8, 3. So those 3, the easiest one, the natural charge of aluminum is a plus 3, but it can also assume different charges. That's why they're called transition metals. That's one of the reasons.
Am I looking at the periods or the groups?
You're looking at the groups. You have to look at the groups for the charges.
Doesn't go minus all the way up?
No, because it is not
Boron is
a...
minus 5, right?
That's right.
Then why is it right underneath?
Boron is a non-metal. Now, that's when it gets confusing when you look at the lines
Oh,
here.
everything past the
Everything
plus
past
3 stays
this,
plus 3.
that's right. Everything that past
okay,
this
I
is
see.
no longer the same family.
So you
Okay?
just go up to group 3 and everything past that is plus 3.
That's not always. Not
So this
always.
side group
Yeah.
3 and then everything past that is plus 3 now?
Not always. Even aluminum is not always plus 3. So we'll have to indicate which one. That's right. On your periodic table, it tells you different charges, right? It's called oxidation numbers. We'll get there when we're in looking at oxidation numbers. But for now, if it doesn't tell you in brackets, plus 1 for that particular metal. Let's try page 7 because we're looking at 789 first. 789. Okay, practice. Magnesium chloride. I think you're just looking at chemical formula. Okay, so let's kind of just straight into the chemical formula, not the equation. What is magnesium fluoride? How do we know for sure? I'll just put plus 2 and minus 1, so that way you'll know which one comes first and you know the numbers that go on the subscripts, right? So magnesium is a 2, chlorine is 1, so that's nothing there, and this becomes Cl and a 2. Okay, and so that way it eliminates your sources of error if you do that. So barium again is a plus 2, nitride negative 3. So then you'll put barium first, and you have 3 there, so I'll put 3 here. Are we okay? And then nitrogen is N, and the 2 from barium goes down there. Is that okay so far? One more on this page. Sodium is a plus 1.
Why are you putting the 3 beside the barium?
Oh, they will switch. They always switch. That's called the
Oh,
crisscross.
because that's what it needs to.
That's what it needs
for that
to.
last building
That's
type
right.
thing?
So barium is actually going to give away two.
Okay,
Two
that's why they
to
switch.
nitrogen. So nitrogen took that.
Yeah.
Yeah. Sodium plus 1, sulfide, negative 2. Okay. So here's what happens again. What was the question? That was a good question. Sulfur is going to take 2, remember? And sodium's going to give away 1. It's going to give away to sulfur. And sodium is going to switch, right? So sodium is going to take the 2, and sulfur is going to have just 1. That's it. They switch. That's what we call the crisscross method. Okay, so what you have here is, this is the formula, and these are the names. And the equation, I can also go this way. I'm just going to expand this, okay? I can also write this the other way. So I can go Mg 2 plus Cl negative. It looks like the opposite way, because look at this. I'm going to just turn to page 8 for a second here. We started with ions as the reactants, and then the compound as the product. You can also go the exact opposite. This is what happens when you put these things in water. So I could take magnesium chloride, for example, put it in a glass of water. That magnesium chloride, which is Epsom salt, you know, you could buy this at the store. It's bath salt. Put it in the bath. Okay, that's an example of it. Magnesium sulfate, magnesium chloride. So you put it in your pool, okay, or your bathtub, you're swimming. This is what happens. It breaks apart into Mg2 plus and Cl minus. Right away, soon as it touches water, they break up. Okay, so this is called, and we'll talk about this later, it's called a decomposition reaction, a dissociation. They break apart, they decompose, as opposed to a synthesis. When you synthesize something, what does that mean? What is a synthetic? If someone says synthetic, you make something, okay? Synthetic is something that's made, right? Like synthetic material. It doesn't occur naturally, it's made. So this, you made something, this one you break it up. We'll get into that. We'll actually do a lab and figure out the different reaction types. So far so good. What about this one? This time you actually have ions already. This one's easier because this is the one that we started with, right? So I'm pretty sure if I give you 1 minute, you'll be able to do page 8 on the bottom. If I give you 1 minute, just the speed of your writing. Okay, let's do it. 1 minute. Doing this one here. Make sure you reduce if you can.
Yeah, you can.
So just the formula, okay? If you did the equation, that's extra practice for you, but we're just gonna write the formula for this one. Is that it?
Yeah.
Okay, reduced, right? Because Mg2O2. How about this one?
GAAS.
Gas. Remember, you remember that you put the uppercase, okay?
Yeah.
The first letter, you notice this, all the first letters on the periodic table is a capital letter, okay? Capital letter. If it has 2 letters, the first one is capital, the second one is a lowercase. Here, I'll give you an example here. This is an example. Let's say if I have CO, what is that on the periodic table? Is this is an element? This is an element. What do we call this element on the periodic table? This is cobalt. Cobalt is a jewelry. It's a nice stone. But if I go CO,
Carbon, oxygen.
yeah, this is not an element anymore. This is a compound because it has carbon and it has oxygen. This one is the whole thing. If the little letter is following the big letter, it's just an element. This is not a good thing. The first one is nice, cobalt, right? The second one is a poison. Okay? That's pollution. It will kill you if it is a gas that's found inside a building. Carbon monoxide. How many of you have carbon monoxide detector in your place?
I wouldn't know.
Yeah, good for you. Now, this could save lives, and it has saved a lot of lives already. So if you don't have one yet, go home, go check for 2 things. 1, if you have a smoke detector at home, and 2, if you have a carbon monoxide detector at home. If you live in an apartment and you don't see those two things, demand that you get them. Okay? Carbon monoxide is not required by law to be put in apartments, but the smoke detector is required. So we have to have a smoke detector. And the smoke detector should be a box that,
It's a circle.
yeah, it's just,
thingy.
there
I
should
don't
be,
think there's one thing.
I know there's a bunch in the hallway.
Yeah, we have sprinklers in here.
Yeah. And then there's that's a good question. Is there one in this room?
No, there isn't. No. You should demand one.
I should demand one. But they should be in the hallway, right?
Yeah, I think there might be. Yeah, but
That's a good question. Why is there not one here? There's
we have
gotta
black sprinklers. So those sprinklers require. Get heated, and then they turn on the.
Yeah.
There's
Water.
sprinklers.
Yeah, those are sprinklers, as you can see. So we're looking at the safety of this lab. So there's water sprinklers. So that means they must have the detector in them. Yeah, it's built in.
Yeah, it's wax.
Yeah, you think, Doug, it's got to be in there already. So it's not a separate box because these are industrial type. Yeah, so those sprinklers would be attached to a sensor then that will trigger it. So if there's enough smoke, that would be it would be the fire and the heat, right?
Yeah.
Yeah, that's
Yeah.
true. It has a wax inside that keeps the plunger down.
Okay,
And when the wax is heated up,
it will melt it and it will.
the plunger will come up and it'll.
So that's the it's a bimetallic strip, I guess. It will then touch. It will make contact point and trigger it. So yeah, check those at home. Carbon monoxide, you can't smell it, you can't taste it. There's no way that you can detect it with just our senses. So yeah, check. Okay. If you don't have it, go to Canadian Tire or any homeware hardware store and buy one. They're not that expensive. For your life, it's worth it. Okay, so that's how you know the difference, right?
At the bottom there, page 8.
On page 8, yeah.
How come you're not putting in the numbers?
Ah,
They
because
cancel each other out?
they do. Because this is
So
2
if
and
they were-
2.
If one was had like just a 1 charge or whatever, you'd have to put in
Yeah.
the 2
Yeah.
on the other side of a 0 or whatever.
You have to think of a number that you can divide the two numbers with that will divide evenly. So again, this is a 3 and 3. That's 3 there and 3 there. I'll divide it by 3 and it will become 1. So that'll just be GaAs. Gallium acetate. So this one is Ba again, BaS. That's it, right?
Yeah.
All right, so that's just reduced form is what you want. So we are doing well. You guys are doing well. Everyone who were here yesterday got 10 out of 10 on making compounds activity. Okay, so when we talk about covalent bonds now, all right, so those are ionic. Covalent bonds, this is when you use the prefixes, those mono, which we can skip, right? Di, tri, and so on. Okay, you need to memorize those prefixes. Do we already know them? What's number 5? Penta. Very good. What's number 7? Hexa is 6. Hepta. That's I know you've been saying. Okay, one more. 8. Octa. That's easy. Octopus, right? 8 legs, right? Okay, so those are the only times that let's review what covalent bonds. How do we know that it is a covalent bond again? You are forming between negative and a negative, okay? Which means they are non-metals. And there are 2 elements that will automatically give it as covalent. Those are hydrogen and
Oxygen.
carbon, okay? Anything that has hydrogen and carbon, one or both of them automatically covalent. And then you'll have to use the di, tri, and so on. Now, when we talk about some special elements are always coupled, they're always partnered. They're called diatomic. Diatomic meaning di means 2, right? So that means there are 2 atoms always bonded together. Okay? It's very hard to break the bond because it's a strong bond. So what do you think would be the number of bonds that these diatomic molecules have? Would that be single, double, triple? What do you think? Would they be single bonded?
Double bonded?
Yeah, some are tripled and some are doubled. Okay, so they're very strong bond. You just can't break them. You need a lot of energy to break them. So an example. Now I don't know what that is. I don't use that. What is that? It's not even a mnemonic. So how I remember it is anything that contains hydrogen, anything that contains oxygen and nitrogen. So that's I guess I think of my husband when I remember this, and the halogens, Han, right? Han, and my kids, I call them honey. So halogens, you look at the halogens, so those are the fluorine, right? Chlorine, bromine, and iodine. Look at the very bottom, the largest halogen. Look at that one, astatine. Why is it not a diatomic molecule, you think? Can you take a look at the periodic table and what symbol does that have? What symbol does it have on the very bottom of that? You see that? Oh, it doesn't actually have the symbol on your periodic table, but it is a heavy element. Does that one? I think that one. I like this one. See that on the bottom there? Okay. It is, yes. So it actually is not really common, and it's not a diatomic molecule just because they don't like to bond necessarily with each other all the time. Okay, so those ones, HON, and most of the halogens except the largest one are always diatomic. So that means these are always H2, O2, N2, F2, CO2, Br2, and I2. That's what diatomic molecule is, right? So, 2. Yeah, nitrogen. So let's take a look at the air that you breathe. What is the chemistry of the air that you breathe? You know what's in the air? What's the majority of? So there's oxygen, that's what makes us alive, right? But nitrogen is the main component of this air. It's about 78% of our air is nitrogen, and it's in the form of N2. Okay, and then followed by oxygen, which is about 20 to 21%. So where are we at? How many percent already? So we're at 99% already, right? So what about the remaining 1%? We have trace. We call it whatever location you're in. So it would be stuff like sulfur. It would be carbon dioxide. Okay, what are the things that are found in the air that make up that 1%? Well, carbon monoxide would be one, which would be very bad, but mostly CO2. See, the difference between CO2 and CO is huge in terms of the toxicity of it, right? CO2, you're breathing out CO2, but you guys probably, how many of you have first aid CPR certificate? Okay, so you know about mouth-to-mouth resuscitation, right? If you have no other choice and somebody stopped breathing, right? You ask them first, may I help you? And if there's no response, and you know your judgment, you got to use your judgment that the person is going to die without your help, right? You got to get someone to call 911, but if they're not breathing, you got to position the head and start breathing through their mouth. Now, you got to think that. You got to think of yourself too. You don't know this person. They may have something that is very contagious, which you could end up getting, right? So you got to think of your safety as well. So if there is a barrier that you could put on their mouth, they do have now a mouth-to-mouth resuscitation barrier. Like if you're a paramedic and you 911, the ambulance comes in, they actually have a machine that they put in your for mouth-to-mouth resuscitation. But what would you do? Now we're talking ethics, right? What would you do if someone's on the ground, not breathing? Would you put your mouth in their mouth to do mouth-to-mouth resuscitation? Again, that would be your own judgment, right? I don't know. It's emergency. So you have to think fast. So what are the trace elements in the air? Well, CO2. You know that mouth-to-mouth can actually survive, help that person survive. So you do have a lot of CO2 that is coming out of your breath when you breathe out. That is mostly CO2 because you've used up the oxygen, but there's still a little bit of oxygen left. So You're talking about air, which is mostly nitrogen. So when you breathe into a person's mouth, yes, they can actually temporarily, that can help them, okay? At least get the breathing going again. Then of course you gotta, if the pulse is not there, then you gotta do the pressures on the chest, right? So yeah, so CO, there's sulfur, there's carbon monoxide, and many other things that are found in the air, depending on where you are. Adam?
How does our body struggle?
How can we have oxygen coming out of our air?
Yeah.
Oh, okay. So you do use oxygen, right? So what happens is you have when you put oxygen into your lungs then will take that into your cells through your blood for your cells to use the oxygen, right? And then your blood will pick up the CO2. So most of the breath that comes out of your lungs when you exhale is mostly CO2. So if there is any oxygen molecules left in there, it would be very, very little. Yeah. Your lungs always have air in it. You can never empty your lungs. It's kind of like a balloon. They actually never completely empty. Even after you take, even if you take all the breath out of your lungs, there's always we call it residual air in the lungs. If they do touch, that's interesting. If your lungs actually touch, there's something wrong with your lungs. It will be hard to inflate it again. That's called collapse. Yeah, so then we're talking about biology there too. So this is the air, the diatomic molecules. Now, you see mostly nitrogen, right? You know this nitrogen here, so you've got this N and you've got this N. Do you guys remember how many bonds are in between? Can we think? Okay, you got how many? I'm gonna give you 1 minute to think this through. We're going back to Lewis dot. Let's go back to Lewis dot. Let's review. You got nitrogen, give me, yeah, you remember? Yeah? How many electrons on the outside of nitrogen? 5, right? So if you have N2, each one will have 5. How many total electrons altogether? 10, right? So 5 times 2, 10 electrons altogether, right? So we put N here and go 1, 2, 3, 4, 5. And then we put another nitrogen here and we go 1, 2, 3, 4, 5. So now we're going to start moving these electrons to make themselves stable. So this will move here. There you go. This will move there. There you go. That will move here. And that will move there. And this single one will move here. And that would be as stable as they'll get. And these will stay there, and this will be a non-polar because you have 2 and 2. They will actually rearrange themselves like that. Or 2 here and 2 there. Okay? It's kind of like a seesaw. You gotta go 1 here and 1 there to make the seesaw stable. You're not gonna put 2 here all together, then the seesaw will be like this, right? Teeter-totter. Yeah, so it is a triple bond. It is hard to break that. You can imagine, this is a science class. Scientists are the most imaginative people I know. And people say artists are, and they're all artists, right? So imagine the nitrogen molecules, diatomic, 2 of them, like 2 nitrogen molecules attached together with a triple bond, just vibrating in the air, vibrating. If it gets warm in this classroom, they vibrate faster. It cools down when we leave at night, it slowly vibrates still, right? Heats up, they go faster. That's what they do. They're very hard to break. But if you do break them, you got N here, you got N there, you got those radicals, and that is good fertilizer. So the N2 is really not a good fertilizer, meaning for the soil. So the nitrogen molecule from the air has to get to the ground. The N will then go into the soil, right? And then this will go into the grass, and this will go into the animal that eats it, and then that will go into the animal that eats that animal. And that is, guys, this is the form of our DNA.
Is there less nitrogen in the air during the winter?
No, there isn't. We'll talk about that. That's called oxygen you're talking about. But pause the thought for a second. That nitrogen molecule that came from the air that is actually attached is what gives us what we are. Nitrogenous base of our DNA. That's what makes you a living thing. Now, how do you think that triple bonded nitrogen diatomic molecule breaks apart? There's got to be something powerful in nature. Something powerful that gets filled up with a lot of those electrons that eventually they need to go back home to the ground. What am I talking about? Lightning. Okay, so when water gets heated, it goes up, right? Neutral water molecule. And then they rub against each other and they become negatively charged. Now you've got all these electrons and they're looking for a way back to the ground. And so they strike this nitrogen with a triple bond. This 1 million volt of electricity coming from one single lightning bolt can be strong enough to break this bond. And now you have this simple nitrogen that will go into the soil that will fuel all that life cycle. Then the grass will use that. Bacteria will then convert that too, but mostly lightning. So what's the world's best fertilizer? Lightning. It's not manure. It's not poop. It's actually lightning. Not interesting. Okay, so those are the diatomic elements. So these are these covalent? Looking at it? Can you tell which ones are which? Without looking at your periodic table, are we able to now look at these? Yeah, how do we know? Carbon right away. Every time you see H or C, automatically covalent. Don't even think about it. You see a C, not a CO though, big C. So this would be covalent. What about, I'll just put C, okay? I and C, because I'm getting lazy now. What about the second one? Covalent again, this one? Ionic. Why? What the covalent part is the OH, right? But this whole thing is still ionic. Okay, so when I saw oxygen there, when I saw hydrogen there, the covalent part is just between the O and the H, so I had to define that. But this whole thing is actually still ionic. Okay, what about that one? Last one. Where's phosphorus? Take a look. Where is phosphorus? Yeah, that P and the big B, don't confuse that with this is PBr. Don't confuse this with this. Okay, you know what this is? That's called plumbum. Plumbum. It's a bum that's dipped in plums. Okay, that's actually the historical, again, that's Latin word, right? Plumbum is lead. That was just a joke, the plumbum. Okay, so the binary covalent, these are the prefixes that we talked about again. I think you guys are very much trained in all these. All right, the last thing that we're going to look at, these are the naming. Okay, so these are the covalent compounds now, right? So we're going to name, we're on page 13, and so that's just naming, and then we're going to get into the words that are going to be converted into formula. Let's do one example of the bottom first, and then we'll go back to the one on top of page 13. Can we take a look at this one first? Let's pick number 3. Okay, so what is the element that we're talking about here for number 3? You get nitrogen and oxide is oxygen. So I'm gonna put N for nitrogen, and then we look at the word tetra, which is 4, and then you got oxide, which is oxygen, and you have deca, 10. That's a big element. So if you were to draw this, you're gonna have 4 nitrogen and 10 oxygen all around it. That's a lot. It's a big element there. It's a big compound. Okay. You want to try this? I'm gonna give you some time, and I think you guys are getting really good at these things. And if you are done with this on the bottom, Those are now putting them into words, okay? So we're going back and forth here. And we're ready to balance equations in by Monday. Okay, let's finish page